Well, good morning or good afternoon, students. This is Mr. Kinney, and we're going to go over the last part 3, questions 29 through 46 on the Unit 2 test review questions. So let's get going on that. So let's see, we finished up the other one. Let me get over here. So you will be provided on your test with a periodic table. Oh, naturally, mine's not here. Right there it is. Should be close at hand. So what is the heat of fusion of water in either, now it can be either calories or joules. So when you look on your periodic table, here's the heat of fusion in water. It's 80 calories per gram. Or if we're using joules, it'll be heat of fusion of water, 334. I think on our test we're going to probably provide you with any heats of fusions you need, but there they are. Also then, what is the heat of vaporization of water? Now it takes a lot more energy to vaporize or to condense water, and it's 540 calories. 540 calories per gram. Or if we're asked you to do it in joules, it'll be 2260. So 2260 joules will be that. So now number 31. So now what that is, if you're using heat of fusion of water, that's going to be when you're down here on the graph. Let me back up. Here's, if you're ever calculating how much energy to either freeze or melt water, you're going to use Q equals mass times delta H of fusion, freezing fusion. Think of the two F's there. If you're working up here at the higher energy where you've got vaporizing, boiling if you like, or condensation, the equation for this will be Q will be equal to mass times the delta heat H of vaporization. Okay, so that's what equations you need to use when you're melting or freezing, boiling or condensing. So now let's get back to our questions. So 31, how much energy is needed to melt 500 grams of ice at 0 degrees? So 500 grams of ice, that's going to be down here. We're going to use mass times delta heat of fusion. So the equation Q equals mass times delta H of fusion. Now the mass is 500 grams in our problem, so we're just going to put 500 grams. Oh, and make sure, I want you to realize delta H fusion, that is just one value we're going to put in. It's 3 words for one thing. And since now on the test, if all the answers for heat of fusion are in calories, you want to use the 80 calories per gram. If all of the answers on the test are in joules, you'll want to use the joules there, okay? I'm just going to calculate it for calories. If you're going to use joules, the answer is going to be about 4 times bigger. So we've got mass times heat of fusion, that'll be 80 calories per gram. Oh, sorry, calories per gram. Calories over gram, sorry about that. Or, now you can multiply it out. If you set it up the other way, okay, you could have 500 grams times 334 joules per gram. So either one of those will get you the right answer depending upon the test, if they want the answer in joules or calories. Number 32, how much energy is needed to vaporize? Now you need to make sure you know that means boil. So now we're working on the top part. This is where, if we're going this direction, adding heat, this is going to be vaporize, also known as boil. If you're removing heat energy, that's our condensing. But we're talking about boiling. Oh wait, let me back up to number 31. So now we've got whatever answer you get, we got to ask ourselves, is this going to be a positive or a negative value? Oh, yes, I posted attendance alarm, thank you. Is this going to be positive or negative? If we're melting ice, okay, that means we're adding energy into the system. So whatever our answer is, the Q will be a plus Q. Q will be plus. We want the positive answer. The test, you may have a negative and a positive. You got to think about it. So now, over here, we're vaporizing some water. So we're going to use Q equals the mass times the delta heat of vaporization. And you know what? On your periodic tables, look at it. It shows you right here. The heat of fusion, latent heat of fusion equation, or the heat of vaporization. We're using this one here right now. And we're going to be using these values here depending upon whether you need to get the answer in calories or in joules. So the mass here is 500 grams. times, and I'm going to do calories first. We said in calories, the heat of vaporization, it takes 540 calories for every gram of water to vaporize it. Or you could have 500 grams if you did it that way. If we're looking for calories, if we're looking for joules, then you'd have to multiply it by 2,260 joules per gram. That's how many joules of heat it takes to make 1 gram of water vaporize. Now, since we are vaporizing, we're boiling, we're adding heat, Q, the answer will be positive. So we want to pick the positive. If this problem was asking about condensing, everything would be the same here, except you'd have to say if you're condensing, you're removing heat, Q would be negative. Same up here. If we were freezing, we were removing heat on problem 31, you'd have to say, okay, we're taking heat away, Q would have been negative if we're talking about freezing there. Number 33, during a phase change, on this graph, these are the phase changes, melting, freezing, boiling, condensing. What happens to the temperature? Well, look at, here's temperature. It's not changing. No change. No change of temperature. That's why we have to use these two equations. And the reason is, down here, you're either using energy to connect crystal lattice bonds together or you're breaking apart the crystal structure. Over here, you're having to use energy to rip apart the water molecules into steam, or if you're condensing, you've got to grab those steam molecules and shove them close together to connect them into a liquid. It takes energy to do that, but the temperatures won't change. How many calories are in a food calorie, also known as a kilocalorie? Well, there are 1,000 little c calories, that's what we use in class, equals 1 capital C calorie, also known as a K calorie, kilocalorie. So that's the conversion factor if you needed to convert that. That's what we use in the food industry because it's just more convenient than writing the hundreds of thousands or millions of calories that would be in our food. So number 35, this is about Q. When calculating heat, if Q is positive, okay, if Q is positive, this is the system, S-Y-S-T-E-M. If this is the system and Q is positive, that means we're adding heat into it. So heat was added to the system. And if you're adding heat to the system, if you're putting heat in, if it's a solid, liquid, or a gas, then delta T will also be positive. If it's a solid, liquid, or a gas, if you're adding heat, the temperature will increase. When calculating heat, if Q is negative, so that means the system has energy being removed from it. Okay, so you're removing heat from it this way. That means the heat was lost or exited the system. And it will be delta T if you have it, the change in temperature. If it was a solid, liquid, or a gas, it would be negative on there because your delta T would be negative because you're lowering your temperature. Oh, way too much. Didn't mean to zoom out that far. Sorry. All right, coming on over here. When using the equation MCAT, Q represents heat, and it'll either be in calories or joules. Label the graph above. Okay, so on this graph, you have a solid. Down here, this part is a solid. Let me zoom in there a little bit. This will be a liquid. And this part of this diagonal will be a vapor or a gas, if you like. So, oh, I put VAS. Oops. V-A-P-O-R, or a gas if you want to think of it. Let's see, what else were we supposed to do? Okay, if you're going from a solid to a vapor, that means you are having to melt and then boil. You are adding energy into the system, which would be water. This would be endothermic. Energy is entering the system to change a solid into a gas. If you're going the other way, if you've got steam super hot and you're going to cool it down into a solid chunk of ice, you're removing energy. This is exothermic. Q here would be negative because your energy is exiting, you're removing it. Endothermic, Q would be positive. All right, I think we did that. Number 39. Define and diagram convection. Well, convection is when you're adding heat, and let's put heat down here. I'll try to diagram. You got heat going on down here. What happens is the heat makes the molecules move faster, spread apart. They move apart, or expand, we can say. And when matter expands, when it gets a little bit bigger, the water will actually get a little bit bigger. It expands. That means its density decreases. The density gets smaller, and now what happens? This low density stuff, they will begin to move up. So low density material moves up. When it cools up here, you have cooling happen up at the top. When you have cooling happen, the particles, these particles get really close together again. So they shrink. So the particles, cooling happens, all the particles get close together, they shrink. That means their density increases. And if their density increases, now they're going to begin to sink. So you get cooling occurring, you get higher density, it heats up down here, and it moves these apart, and so you get those nice little convection currents going like we saw in our lab. So convection, and I always said put an arrow right in the middle of V. That's the one where you've got arrows going in these little cycles like this. This would be where cooling's occurring. Over here would have to be where heat's happening, okay? So, diagram conduction. Well, conduction is when you have either a solid, or maybe even this end of the metal, maybe this is beginning to melt a little bit so they can move around, but you're adding energy over here, and the energy is pushed from one to the other, and then the energy can fly out over here. Maybe you can shoot off and like what to do with a little click-clack demonstrator. But conduction is, both of these are in matter. You need to have matter to pass the heat energy. Here it's by directly hitting each other. Here it's because hot materials rise, and then when they cool, cool materials sink, and you get a pattern going. Radiation, well, no matter. There's no matter involved, okay? Like you're in space, and even here on Earth. So there's no matter involved, and this is when energy is transferred, and I'm going to draw curly in by waves. Radio waves, heat waves, infrared waves, like that. So this is energy transfers, it's through space. Now this energy, when it hits something, let's say if you hit an atom over here, that energy hits this, it gets absorbed, and it's going to make this atom move a little bit. At that point, when you've made this atom move a little bit, that's kinetic energy, that's heat, and we call that infrared, and it makes it get hot. So energy can be traveled through waves, and when it hits matter, the matter gets converted to heat, and it feels warm. Diagram seafloor spreading. Well, we've got mantle down here, and it's hot in the middle part of the Earth. So it makes matter rise because, as we talked about before, this magma gets hot, it expands, and it rises. Up at the top where the crust is, this would be like in the middle of the Atlantic Ocean, it hits up here, it gets cool. Now the crust kind of pushes it aside, and now it's going to begin to sink because it gets cool up here. And then you get this little pattern repeating. And sometimes some of this bubbles out, and you got little volcanoes here. Mid-Atlantic Ridge. And like places like Hawaii, you get weird little things like that happening there. But so let's see, diagram seafloor spreading, and the seafloor moves the same direction as our little convection current. So it's just a convection current under the Earth. So the ring of fire. So the ring of fire, in one of our reading passages, we talked about, because over here in the Atlantic, we've got that little snake of the mid-Atlantic ridge pushing things out, diverging away from each other. What happens is, if you're pushing the world apart here, it has to be absorbed somewhere. And along the Pacific, all along here where all these volcanoes are, we've got the Pacific plate is being shoved underneath these continental plates. And they call that the ring of fire because when that happens, you get earthquakes, but volcanoes everywhere happening. So let's see. How does the ring of fire support plate tectonics? So this, meaning the ring of fire, is where the expanding seafloors push crust under. Push crust under the continents, and when that happens, when the crust gets pushed under, you get volcanoes bubbling up, and you get earthquakes, and you get a lot of volcanoes, and so you get the ring of fire. Heating a balloon to the point that it floats up and away. So, okay, we've all probably seen pictures of the hot air balloons. They're sitting on the ground, putting fire in here. Is this going to be, okay, so when this thing begins to rise up, is that going to be conduction, radiation, or convection? Well, primarily, it's going to be convection because you're making these molecules get hot, they spread apart, and the balloon becomes lower density compared to the air, and it's going to rise up. So you're making this like a little, and when the balloons get up to a certain point, they stop rising, they start blowing in the wind, and if they cool down, they'll sink. Usually the people inside will allow cool air in that makes them a little bit heavier, more dense, and they'll sink back to the ground. So a balloon would be hot air balloon. Anything rising in hot air is going to be a type of convection. Let me fix the focus there. An astronaut on a spacewalk. Okay, they're in space. There's no air molecules. Opens their sun visor, and they can feel the warmth of the sun hitting them. Well, that's going to be radiation because those radio waves, those energy waves travel from the sun. There's the sun right there. And then the astronaut's face over here, they're in their space helmet. Those rays, they can go through their helmet, and then when it hits the astronaut's face right here, it can convert into heat. So that's going to be an example of radiation, the energy traveling through space, and then when it does hit the astronaut, it makes heat, which then you can feel. So we can get that. You grab a handle on a pot of boiling water, that's supposed to be and, you get burned. Okay, that's conduction. Okay, you've got fire over, this is supposed to be fire. You've got your pot sitting right here, and because the metal's inside of here, they're transferring that heat right through the handle, and then you grab it with your hand here. Yeah, that's my diagram for a hand. Ouch, that energy is transmitted through this material to your hand. So with that, goodbye.